Hello, the title of this course is Control System Design, and in this course you would learn about feedback control of single input, single output linear time invariant systems. In order to design and analyze the control systems, we shall use transfer function based representation of the linear systems and would therefore perform our design and analysis primarily in the frequency domain. So, this course would be of interest to students from a variety of disciplines because control systems is essentially an interdisciplinary subject. In particular, the content of this course assumes that the student from whichever discipline he or she is from has already had one course either in control systems or in systems theory, and therefore has been exposed to the notion of a transfer function and to Laplace transforms. So, I would imagine that students in their third year of undergraduate degree and up, including master students and PhD students, would be able to appreciate the contents of this course. We would start this course with an introduction to linear system theory and refresh the fundamentals of Fourier transforms and Laplace transforms. Subsequently, we will introduce feedback control and justify the situations under which one would want to use feedback control in order to control a system. Having talked about the motivation for feedback control, we shall then undertake feedback control design where we have only one controller available for us to design. Such control systems are called one degree of freedom control systems. So, we shall undertake design using Bode plots, Nyquist plots and root locus, and we shall introduce controllers which are already available and are commonly and popularly employed, and we shall also look at how we can synthesize our own controllers. In each of these cases, we will progress from a simple controller structure to a more sophisticated controller structure, and at each point we will justify why we need a slightly more sophisticated control structure in order to address the slightly greater challenges that are imposed by the specifications that have been given to us. Despite the versatility of one degree of freedom control systems where you have one controller available to you for tuning, there is only so much you can do with that single controller. You can do better if you have one more controller available to you for tuning, and such a control system is known as a 2 degree of freedom control system. So, after discussing design of 1 degree of freedom control systems to track references, to reject disturbances and so on, we shall then move on to 2 degree of freedom control systems which can handle problems that are not possible to handle using 1 degree of freedom control. We shall first look at how to achieve robustness against variation in plant parameters using 2 degree of freedom control, and towards this end we shall use root locus based design. Subsequently, we will introduce a new tool which is called as a Nichols plot, upon which we can once again do design in a manner similar to Bode plots and root locus, and we will introduce a new technique called quantitative feedback theory, which we shall use to do more advanced 2 degree of freedom control design where there are multiple specifications that have been given to us, which might include rejection of input disturbance, output disturbance, achieving robust tracking of certain references and so on and so forth. How do we rationally incorporate all the constraints imposed upon the controllers from these different performance specifications and subsequently execute the design of the controllers is something that would be discussed under this topic of quantitative feedback theory. So, with this we would stop with discussing the different tricks and techniques that are out there for design of feedback control systems in the frequency domain, and then look at some of the fundamental properties of feedback control systems. So, mathematics is the language of feedback control, and hence there are certain theorems in mathematics that feedback control systems have to necessarily obey, and these theorems in turn impose restrictions on what we can accomplish as engineers. Many of these important restrictions were uncovered by H.W. Bode, and we shall therefore discuss in this section some of the important contributions in association with the fundamental properties and limitations of feedback control systems. This includes our discussion on Bode's gain phase relationship, the ideal Bode characteristic, and Bode sensitivity integrals. Now these fundamental properties of feedback systems also shed light on why it is difficult to control some kinds of physical systems, in particular physical systems which are called as non-minimum phase systems. These include systems with right half plane zeros or time delays. So we shall then see why it is that it is difficult to control systems with right half plane zeros or time delays, and subsequently also look at why it is equally challenging to control unstable systems. So the last couple of lectures would be devoted to discussion on the challenges that we encounter when we are trying to control systems with either time delay or non-minimum phase zeros or unstable dynamics. At the very end of this course, we shall see how we can extend some of the concepts that we would have learned in the course of the 30 odd lectures to analyze approximately the effect of nonlinearities on our control systems. So although the entire course is focused on control of linear time invariant single input single output systems, in the last lecture we shall see how we can extend approximately some of these concepts in order to control systems that have nonlinearities in them. With that we would conclude this course. So at the end of this course, the student would be expected to be comfortable with design of 1 degree of freedom control systems, design of 2 degree of freedom control systems, and would have a comprehension of what the fundamental properties and limitations of feedback control systems are, regardless of which particular controller we might choose to employ, and subsequently be able to understand why it is difficult and challenging to control non-minimum phase systems and unstable systems. With that, the course will come to its end.